Hello everybody, this video is going to be a continuation of us learning how to use heating curves. This time we're going to be doing calculations with those curves. So let's get started. So you should have this as a glue-in. I went through and tried to make like a finalized version. I took a screenshot so you can ignore the little squiggly lines, right? It thinks that there's typos, okay? I tried to label the line segments with numbers 1, 2, 3, 4, 5 because that's how we're going to label our work. That way when people look at it, we know which section you are working on. I labeled the freezing point and boiling point for water. If it wasn't water, it would have different values. But the freezing point always occurs at the temperature where your first plateau is. And boiling point is always where your second plateau is. You can see as we go up, we heat it, we melt it, we heat it, we vaporize it, we heat it. If you're going down, you cool the gas, you condense it, you cool the liquid, you freeze it, and you cool the solid. Sometimes people have some conceptual issues with the idea of heating up ice without it melting. Or how can you cool ice down? Once it's ice, how can you make it colder? Well, we can have things at negative temperatures, right? You could have ice at -50 and -10. It's warmer ice at -10, but it hasn't melted yet, has it? It's not all the way to 0 yet. So you can heat and cool your solid without it melting. I think sometimes our real life experience with how ice melts and how things freeze and how things boil can kind of mess us up a little bit. So be a little bit careful on those concept questions. One thing that's going to be super important is that because we have all these various segments where we have to use different equations, we have some with MCAT. If you look, all of your sloped lines use MCAT. All of your flat lines use ML. We cannot do one big giant calculation. If I'm trying to go from -50 to 200, I cannot do one calculation. I have to do one line segment at a time. I have to do line 1, and then I do line 2, and then I do line 3, and then I do line 4, and then I do line 5. I have to split it up. I'm going to have 5 separate equations. I'm going to have 5 sets of answers, and then I can add them all together to get my final answer. The part that people tend to struggle with the most is the delta T's. You need to be careful with your delta T. We only do the temperature change for one line segment at a time. If I'm working with line 1, I only look at the temperature change that happens on line 1. I don't care if I'm going to end at 200 degrees. My final temperature for line 1 is only going to be dealt with in this segment. So line 1 ends at 0 degrees, right? When you have line 3, it starts at 0 degrees and it ends at 100 degrees. But you may not go all the way to 100. Sometimes you may stop early, right? Sometimes maybe you're going to start, somewhere in the middle of a line segment. So you need to be a little bit careful with your delta T values. One thing that's important is to understand what's happening at the corners and understanding what phase exists, because sometimes that can be a bit tricky for people as well. So let's look at what phase is present in each piece of the heating curve. So when we're on the first line segment, you only have solid. So for example, you would only have ice. When you get to this corner, the first corner, you still only have solid. You're at 0 degrees because that's the melting freezing point of water. You don't have any liquid yet because you have not undergone any phase change. When you're on line 2, you have solid and liquid present. Imagine a beaker of ice water. They're both present at the same time. you have to undergo the entire phase change. When you get to the next corner, now you only have liquid at 0 degrees. Then you start to heat up the liquid. On this line segment, you only have liquid. You get to the next corner, you only have liquid at 100 degrees. You do not have any gas vapor yet. You have not undergone any phase change to turn any of it into vapor. So you're at 100 degrees, but it has not started turning into gas yet. So when you're on the line segment here, you finally have liquid and gas present together. You undergo the entire phase change, you get to the next corner. Once you're on that corner, it's all been turned into gas, and now you only have gas at 100 degrees. Then you can start heating up that gas vapor, and on that last line segment, you only have gas. Sometimes the questions are going to say that you have ice at 0 degrees, and you have to know to start at the first corner. It might say that you have liquid at 100 degrees, and you have to know that you're on this corner here when you start the question. Maybe it tells you that you're going to end up with liquid at 0 degrees. Well, that tells you that you're going to end at this corner here. So people sometimes have a hard time with understanding, wait, how can I have solid at 0, liquid at 0, but not a mixture? And it's because you're either at the temperature before the phase change, or you've completely finished the phase change into the new phase. Okay, so we're going to do some practice problems. There's going to be a lot of stuff going on in these. We're going to be labeling little heating curves. We're going to have several different equations. We're going to get a bunch of different numbers. So please make sure that you follow along and do things the way you see me do them. Make sure that you're adding in your little explanations and annotations and things, right? Since these are notes, it's not just a worksheet. We're trying to make sure we're capturing enough information to understand what we're doing. You should have a glue-in with these 4 practice problems on them. We're going to start with number 1 and go all the way to number 4. All right, so what is the energy needed to melt 326 grams of ice and heat it to 100 degrees? So I'm going to rough sketch a little cartoon heating curve. I'm going to plot the point of the temperature at which I start and where I end. So it tells me that I have ice, but it doesn't tell me a temperature. So that tells me that I'm at this corner here. They assume that if we don't give you a negative temperature, that you are at the corner exactly. We're going to heat it to 100 degrees, but it does not tell me to vaporize it. So it does not give me any clues that it's going to be a gas, which means I'm going to stop at this corner here. I'm going to have liquid at 100 degrees. One of the things that's tough about these problems is that some of the information is implied, or lack of information is actually giving you information. So you have to kind of get used to the format of the questions. Next, we're going to list out the line segments that we're going to have to do. If I'm going to start at this corner and get to this one, I'm going to have to go through line segment 1 and line segment 2. I'm going to need to melt the ice, and then I'm going to need to heat the liquid. So then over here, we're going to do our actual calculations. We're not just going to say Q, we're going to say Q2. That tells people that we're talking about line segment number 2. Because it is a phase change, flat segment, we'll use ML. And because line 3 is sloped and it's just a heating portion, we'll use MCAT. The mass was 326. And I have to stop and think about it. Is my latent heat of fusion going to be positive or negative this time? Well, since I'm absorbing, I'm heating up, it should be positive. The latent heat of fusion for H2O, which is what we're dealing with, is 334. If you notice, your grams will cancel and you'll be left with joules, and you get a pretty big number. A joule is not very big. So it's very common to get pretty large numbers for these things. Next, we have the same mass, 326. The specific heat, this time it's liquid, right? So I need the specific heat of liquid water. Now it's time to think about our delta T portion. Remember, delta T is final minus initial. I'm going to look just at line 3. That's really, really important. If I'm doing a Q calculation for line 3, I am only looking at line 3. Well, I end at 100, and I started this line segment at 0. That's going to be my delta T for section 3. So 100 minus 0. Punch that out in your calculator, you get yet one more big number. Now, that's 2 separate answers because that's for 2 separate line segments. But I want the total amount of energy to do both parts of this scenario. So the total Q is going to be the energy it took to melt the ice plus the energy it took to heat that liquid up. So I add these two numbers together and I get another really big number. You could put it in kilojoules, but you don't often bother. If you did, it wouldn't be a problem. Sometimes putting it in kilojoules is nice. Sometimes just using scientific notation is nice. It doesn't matter to me. All right, let's do number 2. Determine the energy required to convert 21.1 grams of ice at -6 to steam at 100. So I'm going to start with my little cartoon picture. I am starting at -6, so somewhere down here, and I'm going to convert it into steam at 100. So here's 100 degrees, and the question is, am I on this corner? Am I somewhere in the middle? Or am I on this corner on the right? Well, if I was on the left corner, I would still only have liquid. On the line segment, I have liquid and the steam and the gas, but I want it all the way into steam, so I need to end on this corner over here. So what I'm going to have to do is I'm going to have to heat up the ice until I get to 0 degrees. Once I'm at 0, I can melt the ice with line segment 2. Then I need to heat up the liquid. And then lastly, I need to vaporize it. Right? We have steam at 100, so you do need to complete that phase change. You do need to go through line segment 4. So as you can see, we're going to have 4 separate Q values to do. A lot of little work over here to show, right? We're going to have Q1, Q2, Q3, and Q4. The first line is an MCAT. The second is ML. The third is MCAT. And the fourth is ML again. So my mass was 21.1 grams. Now, when we're on line segment 1, we have solid. So the specific heat of the solid H2O, what we call ice, is 2.09. Now let's stop and think about our delta T. My delta T is not from red dot to red dot. We don't do the entire delta T. Remember, we are only doing one line segment at a time. If I'm Q1, I am only looking at the delta from this section. This line segment, I'm going to end at 0, and I started at -6, didn't I? So final minus initial, 0 minus -6. You should notice that double negative. You're going to notice that I did not change it into a plus sign because every time I do that, people will ask me, wait, I thought you were supposed to subtract. Why are you adding? Well, if you subtract a negative, it's the same as adding. So you'll see that I will very often kind of stack them like this, just so that people can kind of follow along in my process. If you want to put the plus, that's fine, I don't care. All right, so I calculate that and I get my number. Now I have to do ML. Well, line segment 2 is the melting segment, so that's going to be the latent heat of fusion, and it's absorbing, so it's going to be positive 334. I punch that out, I get an answer. Now I'm going to do line segment 3. So I have the same mass, specific heat of liquid water. Now it's time to think about our delta T. Remember, we're not going from dot to dot. It's not the entire delta. It's just the change in temp on the section of the line that we are on. So I only care about this little section right here. Well, ending on this line segment was 100, and this line segment started at 0. So my delta for this line segment is 100 minus 0. Punch that out, we get our answer. For the last one, now we're on the second plateau. This is vaporization, so I'm going to need latent heat of vaporization. We're absorbing, so it's a positive value. Remember, it's the bigger of the two because it takes a lot longer to vaporize. And you can see that it took a lot more energy to vaporize that than it did to melt it, didn't it? Took a lot more energy to heat the water up than it did to to heat the ice up to 0. So you can always stop and double check that the size of your numbers kind of seem to make sense. Now we're going to add up all of those numbers. And we get our very final answer, nice big number, units of joules because it's energy in a box. If you want to do scientific notation, feel free. If you want to do kilojoules, feel free. All right, so the next one's going to have a little bit of a twist. Okay, number 3. Here's my little cartoon. Now let's start reading the question. What is the heat transfer involved when you convert 51 grams of water, 0 degrees, to ice at negative 20.3? Well, wait a second. I'm trying to end up down there, right? And I'm starting here. This is backwards, isn't it? I'm going backwards. Right? My latent heat's going to be negative. My delta T is going to be negative. My Q value will be negative. I am too lazy to redraw this curve and make it go the other way. I don't care. I'm just going to leave it, and I'm just going to know that I'm going backwards this time. So I'm actually going to do line segment 2 first, and then as I cool down, I'm going to do line segment 1. Now, I'm sure there's teachers out there that would want you to redraw this as a cooling curve. Lucky you, you don't have those teachers, okay? So you can just leave it like this. I don't care. So now, even though this is the first plateau, right? We're used to thinking of that as melting, but it's also freezing if you go the opposite direction. And melting and freezing occur at the same temperature. So it's still at 0 degrees. Q2, Q1 will be down here. Q2 is ML, Q1 will be MCAT. I have 51 degrees, and now be very, very careful. My latent heat is not 334. My latent heat is negative 334. I have to supply the negative sign in order for my Q value to make conceptual sense. This has to end up negative Because there's no delta T portion, you supply the negative yourself. So now let's do the next one. We still have 51 grams. Now we're on line segment 1, so my specific heat is going to be 2.09. Now it's time to stop and think about our delta T. Well, where did I end? I ended at negative 20.3, and this line segment started at 0. So my delta T is negative 20.3 minus 0. Final temperature minus starting temperature, which will end up as a negative, which will force my Q value to also be negative, which makes sense because we're cooling down. We have to let go of the energy. We have to get rid of it. Add your values, you get your number, and stop and think. Does this make sense conceptually? Look, my Q is negative. That's good. Energy was released. Cooling down is exothermic. Sometimes people really struggle with that, right? We think of cold, right, as being endothermic. But cooling is an exothermic process because the system has to get rid of its extra energy. So be careful with your thought process. Always make sure you're thinking about things from the perspective of the system when you're trying to decide if it's positive or negative. All right, one last one. There's a twist on this one. For this one, we're trying to decide what's the energy absorbed when you melt 75 grams of ice at -5 and you heat it up to water at 90. Here's my little cartoon. I'm starting at -5 and I'm going to 90. Right now, you should notice something. I didn't go all the way to a corner, did I? I'm not finishing this line segment. I am stopping early, so you have to be careful. If you don't finish the line segment, your final temp is not 100. So when you do your delta T, you need to make sure you're not on autopilot. Make sure you're actually using the temperature that you end at. Don't go all the way to 100 if we're stopping early. Be careful. So what I'm going to have to do is I'm going to heat up the ice until it's at 0. Then I can phase change it, melt it. Then I can heat the liquid up. We're going to have Q1, Q2, and Q3. Why don't you pause and see if you can finish this all the way? See if you can find your Q total. Be careful that you use the right specific heat and the right latent heats. Make sure that you're being careful about your delta T. Remember that we do delta T based on each segment that we're on. You're not going dot to dot. Okay? So pause and give it a try. All right, let's see how it went. We're going to have MCAT, and then ML, and then MCAT. Our mass is 75. Specific heat of the solid is 2.09. This line segment ended at 0, and we started at -5. Careful of your double negative. Next, we're going to phase change it. We're going to melt it. We have 75 grams. The latent heat of fusion is 334. Positive because it's being absorbed. Next, we're going to do line segment 3. We still have 75 grams. Specific heat of liquid water is 4.18. And now it comes time to stop and think about delta T. I am not going dot to dot. I am only doing this segment. This portion ended at 90. and it started at 0. So 90 minus 0. Be very careful. Make a big note or some, star, exclamation point, something. Q total is going to be the sum of all the steps you had to do. And we get our big final answer with units and our box. All right. So the nice thing about heating curve problems is that no individual portion is super hard. Like, you guys can all multiply two numbers together. You can all do subtraction. You can multiply three numbers. You can add. You guys can do all that. The thing that's hard is knowing where to start and stop, knowing which line segments. And 99.9% of people who struggle with that have a much easier time if you sketch out your cartoon heating curve and you plot your dots and you do it like you saw me do it in the video. People just want to be lazy and not draw it, and there's not much I can do, right? If you're not going to kind of take the suggestions I have. My suggestion is to sketch your cartoon, plot your points like I do, okay? The other part that makes these questions tough is if you make one small mistake in one of your Q values, your final total is wrong, isn't it? Once again, one of the things that we are trying to teach you is how to be very precise and careful through the entirety of a problem. So make sure you understand you are not probably going to get partial credit for Q1, Q2, Q3, and the final answers separately. I'm going to check your final answer. Okay, so you have to be very, very careful and pay attention to those details. Okay, one thing that you might stumble across is that sometimes people use slightly different values for specific heats and latent heats. So I know like one textbook I had 333 joules per gram, or they had 2,240, right? Just slightly different numbers, or 2.07 instead of 2.09. Not a big deal, okay? Use the numbers I gave you in the problem. If there's ever a strange, twist where I want you to use a slightly different number, I will tell you, okay? Not a big deal. It's just if you find random worksheets online, you may see slight variations, okay? For quizzes and tests and things, you should use the numbers that I give you always. Let me show you one more time, right? These ones, this is what I would like you to use on any kind of assessment. This is what will, our program will calculate with. Okay. All right, everybody, that was it. I hope that was helpful. Bye.